So let's proceed. We are saying butane is burned with a dry air fuel ratio of 20. Then calculate the percentage of excess air, the molar percentage of carbon dioxide in the products, and then probably, if time allows, we shall look at the dew point temperature of the products. Now, what we do at the very first stage is to write the chemical equation. Write the chemical equation. For the reaction, so we are going to write, this is butane. We say the butane is also an alkane, and it has 4 carbon atoms, meaning it is going to be C4H10 from Cn H2n plus 2. Carbon is 4, N is 4, so we have C4 H2 times 4, which is H2H plus 2, we get 10. So that means our C4H10 will be butane plus now air. Okay, so we will have oxygen plus 3.76 of nitrogen, and we will produce carbon dioxide. We need to produce water, and we may also have some nitrogen. Let me push it to the end. So our task here is to balance. We already said this is 4.76 kilomoles of air. So we balance carbon is 4 this side. This one should also be 4. What is water? Water is having hydrogen. So hydrogen here is 10. This side is 2. So we put 5 here. So what happens to oxygen? Oxygen becomes, we have 8 here. 8 plus 5, we shall have 13. But this side we have 2. So to make it 13, it should be 6.5. So if it becomes 6.5, what is going to be the ratio? The moles of nitrogen. You get 6.5. You multiply by 3.76, and this is going to be 24.44 of nitrogen. Okay, once you have ascertained that, you have to proceed and now look at the percentage of excess air that we are told to calculate, and that will be obtained from the air fuel ratio. So we have A percentage percentage of excess air. So we already know that air fuel ratio is equal to mass of air divided by mass of fuel. Mass of air, we have 6.5 times this 4.76 times the molecular mass of air, which is 29. We divide it by mass of fuel. So the molecular mass of this butane is going to be C4, that is 4 times 12, that is 48, plus 10, we shall have 58. But how many moles do we have here? Theoretically, it's 1. So times 58. And what is going to be the value here? So I get 6.5 times 4.76 times 29 divided by 58, and we have 15.47. Now, what does this mean? Means theoretical air fuel ratio for this reaction of butane and air to completely produce the products of combustion, that is carbon dioxide and water vapor or water, will require 15.47 more air than fuel. So that will be 15.47 kilomoles of air per kilomole of butane. In other words, the fuel. So if 20 as the air fuel ratio was used, we need to know what was the excess air added. How do we get that? We know that the percentage excess would therefore be the actual air used minus the stoichiometric or the theoretical one divided by the stoichiometric air ratio, of course multiplied by 100. So the percentage excess will therefore equal to, we have 20 minus 15.47 divided by 15.47 times 100. So divided by 15.47. So the answer is 29.28%. So the excess, the amount of air supplied, supplied in excess is equal to 29.28% of the theoretical air. So that would be telling you that in this reaction where they use the 20 as the air fuel ratio, you would have 1.29 times this theoretical one. So in other words, this tells us that the 20 air fuel ratio means 1.2928 times the theoretical air was used. That's basically what it means. So we have answered part A, and let us look at part B. So to do part B, we need to rewrite our equation so that we incorporate in the 1.2928. So now we have done part A. Let us look at how we have done part B. So part B requires us to determine the molar percentage of carbon dioxide in the products. So we have already done the percentage of excess air, and the percentage of excess air, we found out that it was 29.28%. Now, we need to rewrite the equation for the reaction for us to be able to determine the percentage of carbon dioxide in the products. So as we proceed, when you write this chemical equation, you have butane plus oxygen plus nitrogen. We already said this is air, and which is composed of 4.7 kilomoles of air. That is the theoretical amount of air that is available. But then for complete reaction, we need 6.5 moles of this air, of the 4.7. I mean 6.5 times 4.76 of air. And then because we have excess, remember we have used the air fuel ratio of 20, then we have an increase by excess air of 0.2928. So what does that mean? 0.2928 is added onto the original existing air, which was 1 by proportion. So when we add it to 1, we will have 1.2928. So that means the excess, the total air amount that is going to be supplied is going to be 6.5 times 2.2928 times the 4.76. So our products include carbon dioxide and the theoretically, and then even actually 4 moles of carbon dioxide are produced according to this chemical reaction when we have complete combustion of this fuel, butane. Then we will also have water and 5 moles of water vapor present, then plus nitrogen. And we said to get, when we also look at our products of combustion, we have some oxygen present because of this excess air supplied. So we shall also add some oxygen. Now, how do we balance? We already said this is 4 to balance the carbon, the 5 on water to balance the hydrogen and oxygen on this and that. So what is now the portion for this other oxygen that is present? What we shall do is to get the total oxygen here, and the total oxygen we have seen is 6.5 times 1.2928, which gives you 8.032. Then we multiply by these 2, we shall get 16.8064. So when we get that one, we need to now subtract this side. We are going to subtract the oxygen, which is 13. So when it is 13, what we shall get is going to be 3.806. Now that value, we are going to divide it by 2 so that we get a value that we can put here that will balance the oxygen. So when we divide it by 2, because of these 2 atoms of oxygen, we'll have 1.903, and that will be the number of moles of excess oxygen available in the byproducts. What about the nitrogen? It will be 6.5 times 1.2928 times 3.76, and this will be 31.596. Okay, that is the number of moles of nitrogen in the products. So to get the percentage of carbon dioxide in the products, it is going to be the moles of carbon dioxide divided by the total moles of products. The total moles of products, we shall just sum 4 plus 1.903 plus 5 plus 3 point, 31.596, and we shall have 42.9499, and the moles of carbon dioxide are 4. When you do the multiplication, the percentage would come to 9.41. So that is the proportion of carbon dioxide that is present in the byproducts of combustion. Now, part C requires us to determine the dew point temperature of the products. To determine the dew point temperature of the products, we need to analyze the water vapor that is available in the byproducts. So by using Dalton's model of partial pressures, we will have to determine the partial pressure of the water vapor. So the partial pressure of water vapor is equal to the molar fraction of water times the pressure, that is the pressure of the system, and we are going to take the pressure of the system to be atmospheric, and we are taking the value of that atmospheric pressure to be 101 kilopascals. Now our problem is we don't know the molar fraction of water, but we can use the products of combustion up here and the moles that are present. We look at the number of moles of water. So what will that be? We need the moles of water vapor divided by the total number of moles of the products. The moles of water vapor are 5 according to this chemical reaction. They are 5. So we are going to get 5 divided by 4 plus 1.903 plus 5 plus 31.596. And the value is going to be 5 out of 42.499, and we will have 0.1176. That's the fraction of water by moles available in the byproducts. So what will be the partial pressure of this water vapor? It will be the molar fraction 0.176 times 101, giving you 11.88 kilopascals. So to determine now the dew point temperature, we will go to the tables of saturation temperatures. So when we reach there, we will read off the values. We see this is in megapascals, but our value is in kilopascals. So we can multiply this by 1000 to convert it to kilopascals. So the value that we have is 11.88, which lies between here and this. So 9.595 and 12.35 give you a range in which our temperature is going to be lying. So our temperature is going to be lying between 45 and 50. So by interpolation, we can be able to calculate that value and then write it down. So these are our values and the corresponding pressures. Our x that we don't know represents, corresponds to 11.88, and then 50 corresponds to 12.35, and by interpolation, our temperature should come to 49 degrees Celsius. And we said this temperature is very important because should the water vapor condense, or should the temperature of the products reach this 49 and goes below, then the water vapor will condense. So if it condenses, it is undesirable because that water mixed with some other products like carbon dioxide, you get the carbonic acid, which can corrode the components of the system. Also, sometimes the fuel contains sulfur dioxide. Sulfur dioxide, when burnt, sulfur in the fuel, when burnt, produces sulfur dioxide, and that sulfur dioxide, when it mixes with water, it also produces sulfuric acid, which is also corrosive. and it is not desirable because it will affect the components of the system, thereby hindering the general efficiency of the system and the performance of the system. So you have to make sure that you control the temperatures of the products and ensure that the temperatures are above this 49 degrees Celsius. How? You can do it by supplying in excess air and maybe increasing the temperature, supplying heat from outside so that you have this temperature maintained or above. Thank you so much.